Right, so welcome back. Today we want to talk about differential equations. So we're starting Unit 8. So the past 4 units we've been talking about integrals, and now we are moving into the last part of single variable calculus, the last half of calculus 2. That's sort of when we want to discuss direct applications of both differentiation and integration. So we are going to be doing that in differential equations first in Unit 8. Then in Unit 9, we're going to be talking about infinite series. And then in Unit 10, we're going to be talking about parametric equations in polar coordinates, which some may argue is just a prelude to multivariable calculus, but we'll get to that later. So today we're going to be talking about differential equations. So I'm sure that if you've taken a calculus-based physics course, you've heard what a differential equation is. It's what you use to solve pretty much every single problem in calculus-based physics or mechanics, right? But now we're going to talk about it in a more mathematical way. So what is a differential equation? Right, what is a differential equation? So a differential equation is really just an equation where we include the rate of change in the equation. So that's like something like df dx equals f of x. And that's obviously a very easy differential equation to solve. We'll get into how to solve stuff like that later, but it's essentially something where we have a rate of change in the problem. So a great example of that is population growth, or we could have particle motion. There are many things that we could be using differential equations for. So let's go through a couple of quick examples, and this will kind of talk to us about how to solve these things, because it's going to look fairly simple at first, and then we're going to get into some tricky bits later. Anyways, so we're going to talk about population growth and harmonic motion first. So for population growth, let's say that we are looking at a function where the derivative, so dp, the rate of change of the population with respect to time, is equal to some constant times p. So what this is really saying is we have a function f prime of x, and this function is proportional to the normal function f of x. So what function is there that when we take its derivative, it's proportional to the original function? Well, we know that the natural exponential e to the x, if I differentiate e to the x, I get e to the x. But we also know that if I differentiate something like e to the 2x, well, then we're going to get 2e to the 2x with the chain rule. Now, 2e to the 2x is proportional to e to the 2x. So there we have it. There's an example of a function that when we take its derivative, it's proportional to our original function. So we can expand this. So say we want to take the derivative, in our case, d by dt of e to the kt. Well, then that's going to be equal to k e to the kt. And that is proportional to f of t, or p of t. So there we've found a general solution to this problem. So, well, if somebody asks you what function satisfies dp by dt equals kp, well, that means that its derivative is proportional to the original function. We just proved our example right here. Our function would be k e to the kt, as of course that is proportional when taken a derivative of first order. Okay, so now we're going to talk about harmonic motion. So you may recognize this as the spring law. So this formula governs our the way that springs oscillate. So the force is equal to negative spring constant times x. So really, we're going to use Newton's famous second law that says F equals ma. So F equals ma, and a, this is really m times the second derivative of x double dot, which is equal to m d squared x by dt squared. So what we can really write this as is d squared x by dt squared is equal to negative kx. So, oh, and this is times mass, but we can say in this scenario we're setting mass equal to 1. That's going to make this a lot easier, so we'll set mass equal to 1. Then we've got d squared x by dt squared is equal to negative kx. So now what we are looking for a function that when you take its derivative twice, you arrive at the negative of that function. Okay, so, and it is also proportional. So, well, what function, if we differentiate it twice, we get the negative version? So this sounds a lot like what we do when we do trigonometric functions. So let's say we start off with sine of x, then we differentiate once, then we get cosine of x, then we differentiate again, then we get negative sine of x. Well, there we found one where we get the negative, but is it also going to be proportional? Let's try sine of kx. So we'll try sine of kx. Then we go there, then we get k times cosine of kx. And we differentiate once more, then we get k squared sine, a negative k squared sine of kx, and that there is proportional to what we're looking for. So there, that is where we get harmonic motion from this Hooke's law here. So we see that our second derivative is proportional to the negative of the original function. That should immediately be ringing alarm bells that you've got a trig function involved, or at least a sine and cosine. And we could have alternatively done this with cosine. It doesn't need to be sine. Whatever really suits your fancy for if you're maybe dealing with some sort of phase shift, maybe it's easier to use cosine instead of sine. I'm not sure. But anyways, these are the two types of differential equations that are very important when the function is proportional to the original function, or where the derivative is proportional to the original function, and where the second derivative is proportional to the negative of the original function. Because that's for exponentials, that is for trigonometric harmonic motion or oscillation or whatever. So those are the two that I would really urge you to recognize. All right. Well, anyways, now let's go through another example. So we're going to talk about general equations. So general equations is the real elementary basis of differential equations. And what's really nice about this is all stuff that you've learned. We can apply everything that you've learned really in your differentiation rules and, of course, your algebra and trig skills to solve these. So we're not going to be spending much time on them. What we're really going to be spending time on is numerical and analytic solutions later on in this unit that allow us to solve differential equations where you might not be like immediately, hey, I know how to solve this. But this is something that we do know how to solve. So we are going to show that y equals 1 plus c e to the x over 1 minus c e to the x. We're going to show that that's a solution to dy dx equals 1/2 y squared minus 1/2, or 1/2 times y squared minus 1. Okay, so of course what we need to do first is we need to find our derivative. Again, I urge you to pause the video and pretend that what I have written below doesn't really exist. Try to solve it for yourself, but of course if you need some help, we'll solve it together. So we're going to solve the derivative first of y. So of course we need to use the quotient rule. So that's low d high minus high d low over low low. So we get 1 minus c e to the x times c e to the x minus 1 plus c e to the x times negative c e to the x over 1 minus c e to the x squared. Okay, so we do a little bit of algebra, and then we get 2c to the x over 1 minus c to the x squared. Okay, so we've got that. So that's our derivative. So that is y prime. We're going to write this differently all the time so that you get used to the notation. I personally like this dot notation as someone who likes physics and classical mechanics. We like to use the dot notation so we don't get super cluttered. But you could alternatively write that as your dy dx. Anyways, we're going to set the right-hand side. So this is the right-hand side here. We are going, or no, sorry, that's not the right-hand side. That is the right-hand side. We are going to set that equal, and we are going to plug in, our function. Sorry, I just erased that, but there is our function there. We're going to plug that in, so we get 1/2, 1 plus ce to the x over 1 minus ce to the x squared minus 1/2. Okay, so what we do is then we combine everything. We get 1/2 times 1 plus ce to the x squared minus 1 minus ce to the x squared over 1 minus ce to the x squared. We do more combining, and then we get 1 over 1/2 times 4 ce to the x over 1 minus ce to the x squared. And then when we combine those fractions, we can cancel some stuff out, and then we end up back at the left-hand side, thus proving that that is a solution to the differential equation. Okay, so I could have alternatively said, I could have said something like solve y dot equals 1/2 y squared minus 1/2. Now that might be a little bit more tricky to solve, but we do know what the answer is. We found our y. We have our y there, and we have our y dot there. But anyways, the important thing is that here we are going to end up always with some sort of constant. And that's called an initial value problem, because when you solve a differential equation, you find your general solution. You call it a general equation because it's not specifying something of constant order. So I could be given the solution to a differential equation that is something like x squared plus k. So x squared plus k is an arbitrary constant that moves up and down the y-axis. So what we would need is an initial value problem. So you would need to say like something like y of 0 equals, I don't know, something like 2. And then you'd be like, okay, k equals 2, because that's giving us our constant degree of freedom removed. Otherwise, you've got a series of curves like that, and you might not know which one is actually a solution. You would just be given a general solution, so you'd say it's x squared plus k. All right, so that's what we've got for general equations. It's a fairly easy topic, as long as you know what you're doing at the beginning. Otherwise, I guess you want to make sure that your differentiation skills are pretty good and that you've got a pretty good intuition for what these things mean. In the next video, we're going to be talking about slope fields and Euler's method. Then we're going to be moving on to separable equations, which I think is a fun topic. We'll talk about population growth, linear equations, and then finally some predator-prey systems, bringing you into some biology. Then we'll be off to Unit 9. Thanks for watching, and we'll see you in the next one. Bye.